All right, section 6.6, final section of chapter 6, solving exponential and logarithmic equations. There are going to be four different ways or methods we're going to discuss here. Two of them involve exponential equations, the other two involving logarithmic equations. Okay, so we'll start with the exponential equations. The first method, I guess you could say, is the exponential equation property of equality. And what the exponential equation property of equality says, and that's kind of a mouthful, it says this. It says if b to the x is equal to b to the y. Okay, so if b to the x is equal to b to the y, then what we can say about this equation is that x is equal to y. Okay, and that should make sense. If b to the x is equal to b to the y, then we can pretty much assume, or safely assume, that x is equal to y. The one catch here is that the bases need to be the same. That's something we can jot down. The bases must be the same. Bases must be the same. So if these two numbers, the b's, aren't the same, then we can't use this property right away. Now that doesn't mean we can't use it at all. I'll just show you how we have to kind of work around it. So before we do that, I do want to give you a couple of easier ones. So directions are going to be to solve. Number one, we're going to go with 7 to the x is equal to 7 to the fourth power. So when we say solve, we're really looking for the x value that makes the equation true. The question then becomes, are the bases the same? Clearly, we can see that they are, so we can just set the exponents equal to each other, and we're already done solving because x is already by itself. So number one's a real basic example, but that would be an example of the property of equality for exponential equations. If the bases are the same, like 7 and 7, then we can say that the exponents, x and 4, are equal to. Now if this, let's say that this was 2x, 7 to the 2x is equal to 7 to the fourth, then we would have something like 2x is equal to 4, and then we would have to solve from there. Okay? We'll skip the next example in my notes because it's essentially the same thing. So we'll move on to something maybe a little harder now. Number 2, we're going to have 3 to the x is equal to 27 to the 12th power. Okay, so remember what the property says, the bases have to be the same. Right now, they are not, 3 and 27. But what works out here is that 27, we can rewrite 27 using the base of 3. 3 to the x doesn't change because that's going to stay the same. 27, we can rewrite it as 3 to the third power, and then that becomes to the 12th. Okay, so 3 to the third to the 12th power. All I did here was rewrite 27 using a base of 3. Okay, so now what we can do, we can take 3 times 12. So we'll have 3 to the x is equal to 3 to the 36th power, because this is, oops, that's an x. This right here is the power to a power rule. If two exponents are right next to each other, we just need to multiply them together. So 3 times 12, that's where 36 comes from. And now we got 3 to the x is equal to 3 to the 36. Now our bases are the same. Now we can set our exponents equal to each other. X equals 36, and we're done because there's nothing else to solve. So that would be your answer for number 2. X is equal to 36. If you're not sure, you can always go back and plug in 36 in your calculator, 3 to the 36th power. It's a very large number, and it should be equal to 27 to the 12th power. Okay? Let's try another one here. Number 3. We're going to have 100 to the x is equal to 1/10 to the x minus 3 power. All right, so neither of these bases actually are going to stay, but we can write 100 and 1/10 using the same base. That base is going to be 10. So 10 to the what power? So we need to figure out an exponent for up here. 10 to the what power gives us 100? Well, if you're looking at your half sheet, or this might be a fact that you already know, that would be 10 squared. 10 squared is 100, so then we'll have 10 squared to the x power. 1/10. Well, that's the reciprocal of 10. The reciprocal power, or the exponent that refers, or that means reciprocal, is -1. So this will be 10 to the -1st to the x minus 3 power. Okay, so we're rewriting 1/10 using the same base as the other one, and we'll use 10 to the -1st. Okay, so now we'll have 2 times x here, so we'll have 10 to the 2x is equal to 10 to the, and we'll have to distribute here the -1, so negative x plus 3. Now we've got the bases to be the same. We can drop the bases. 2x is equal to negative x plus 3, and we'll have a two-step equation here. We need to get the x's to one side, so I'll take that x this way. So that would be 3x is equal to 3, which then means x is equal to 1. Okay, so our final answer for number 3 here is 1. Let's try one more here. Number 4, running out of space. 6 to the 2x minus 6 power is equal to 36 to the 3x minus 5 power. Again, our bases aren't the same, but what we can do is rewrite them using the same base. The base here that we should use is going to be 6, because this one is already 6. This one is 6 squared. So we'll have 6 to the 2x minus 6 power is equal to 6 squared to the 3x minus 5 power. Okay? I'm going to skip, well, no, I won't skip it. So we'll have 6 to the 2x minus 6 is equal to, we'll have to distribute that. 2 times 3x is 6x. 2 times negative 5 is negative 10. So, bases are the same. Drop them, set the exponents equal to each other. So we'll have 2x minus 6 is equal to 6x minus 10. Now, I'm going to take the variable that way. I'll bring the constant number that way to the left, and we'll go from there. So on the right-hand side is going to be 4x, so I'll have to subtract that 2x. I'm going to have to add this 10 to this side, so negative 6 plus 10 is positive 4. And one more time, we'll just have to divide by 4, and our x value will be 1. Okay? So 4 examples of the exponential equation property of equality. The bases have to be the same, and then once they are, you can just set the exponents equal to each other and solve from there. Let's move on to method number 2, the inverse property of exponential equations. Okay, this one tends to trip people up just a little at first, because it's just something that you've never seen before. There are actually 2 properties here, or 2 examples. So if we have the log base b of b to the x, that is actually equal to just x. Or if we had the natural log of e to the x, that would be also equal to x. Okay, so that's the first half of it. The second half of the inverse property says that if we have b to the log base b of x power, that is also equal to x. Or if we have e to the natural log of x power, that is equal to x. Okay, so if you're taking the log base b of b, the natural log of e, those are all inverses of each other. Or same thing, b to the log base b, e to the natural log. Those all cancel each other out. Okay, so what you're left with then is just the exponent, or just the variable that you are looking for. Okay, so let's do a couple of examples. I've got 3 of them here for you. Hopefully we can start to make some sense of this. So, example, solve number 1. So let's go with 2 to the x power is equal to 7. Now, we don't have a nice number, 2 to the x. There's no way we could get 7. We're using whole numbers, because 2 to the second power is 4, 2 to the third power is 8. So it's going to probably be between 2 and 3, but we'll figure that out once we get there. So to get the x value by itself, we want the x to be alone. What we need to do to get the x out of the exponent side and bring it down to just be a number, what we need to do, since we've got a base of 2, we're actually going to take the log base 2 of 2 to the x power, and if we're going to do it on one side, we have to do it to the other. So it's just like any other property of solving equations. Whoops, I'm going to make that here in black. It's just like every other equation where if you do something to one side, you have to do it to the other. Now we're just introducing a new method, or new operation, you could say, to kind of think about how we can get x by itself. So the log base 2 of 2 to the x. The log base 2 of 2 cancels out. The only thing we're going to be left with on the left side is x. Okay? Now, the log base 2 of 7. This is going to be the change of base property in your calculator, because this is not going to be a nice number. Okay, we can use natural logs or common logs, doesn't matter. I'm going to use common logs. We'll have log of 7 divided by the log of 2. And again, in your calculator, you're going to need to use parentheses. But I'll get rid of those. And what you should find if we round to 3 decimal places, x is equal to 2.807. Okay? Now, what you can kind of think of here is, or if you're asking why does this work? So let's focus on this one right here real quick. We'll do it in green. So the log base b of b to the x power. Okay? If we think about the power property where the exponent goes out front, this becomes x times the log base b of b. Okay, so if we think about this one now in terms of exponential form, b to what power is equal to b? And that means that this whole thing is 1. So we're just left with x. Okay, so that's why it all works. And the ones over here, these similar rules. Okay, so the reason that we're going to do that, do the log base of whatever on each side, is for this reason. We want to get the exponent by itself, and what's going to happen is that the log base b of b is always going to be 1. Okay, so this, it just gives you the exponent, just like we had here. Log base 2 of 2 is 1, so that'd be x times what essentially becomes 1, which is just x. Okay? Hopefully that makes a little sense. If not, it's not a big deal that you don't follow it. Really what I'm concerned is, do you know to take this step? Let's try another one here. Number 2. Let's go with 7 to the 9x power is equal to 15. All right, so what we want to do first is be able to bring this 9x, so it's no longer an exponent, so now we can bring it out front. The way we're going to do that is we need to get rid of this base, and we're going to get rid of the base by taking the log base 7, since in this case the base is 7, of both sides. So log base 7 of 7 to the 9x power is equal to the log base 7 of 15. And if we're going to do the log base 7 on one side, we have to do the log base 7 on the other. Okay, so this log base 7 of 7, that whole thing cancels itself out. We're just left with 9x. Okay, now again, the log base 7 of 15, that's not a good number. You can use your calculator here. Use the change of base formula, log of 15 over the log of 7, and what you should get is about 1.392. 1.392. Okay, so what we really have is 9x is equal to 1.392, and we have a one-step equation from there. Need to divide both sides by 9, and x should be somewhere in the neighborhood of 0.155. Okay, so again, if you're ever concerned that you're wondering if you have the right answer, go ahead and recheck it. So if you do 7 to the 9 times 0.155 power, you should get something in the neighborhood of 15. Now there's a rounding issue here that you probably won't get exactly 15, but if you're somewhere in the neighborhood of like 14.996, you know, that's pretty darn close to 15, and that would be good enough for me if I was checking. Let's try one more. So, number 3, we've got 4e to the negative 0.3x power minus 7 is equal to 13. There's a few more steps involved here with this one. So, first thing we need to do, we need to get the base by itself. E to the negative 0.3x power. We're going to do that. First, we need to get rid of the 7 by adding 7. So we'll have 4e to the negative 0.3x power. Add 7 to both sides. That gives us 20. Okay. Now get rid of the 4. So we'll divide both sides by 4. So we'll have e to the negative 0.3x power is equal to 20 divided by 4. That would be 5. Now that we've got the base by itself, we need to get rid of it. We're going to do that by taking the logarithm of it. Since we're using base e, probably going to want to use this one right here, the upper right hand corner, natural log of e to the x. Anytime we see we're using e, pretty good bet that we need to use natural log. So we'll have the natural log of e to the negative 0.3x power is equal to the natural log of 5. Okay, I'm out of space here. I can't scroll up any farther, so I'm going to have to do this off to the side. So natural log of e to the negative 0.3x. Natural log of e cancels itself out, so we're just left with, we'll draw a little arrow here, negative 0.3x, and that is equal to the natural log of 5. That's something you can type in your calculator. That is 1.609. Okay? We got one last step. We're going to divide both sides by negative 0.3. Divide by negative 0.3. Again, calculator work here. X is equal to negative 5.365. Negative 5.365. That beep was the school bell, by the way. So, 3 examples of undoing a base, or getting an exponent out of the exponent, getting a variable out of the exponent by taking the logarithm or natural logarithm of both sides. That method is going to be very handy when it comes to solving exponential equations. All right, so let's move on to logarithms, logarithmic equations. So, first of 2 methods, the logarithmic equation property of equality. Again, another mouthful. This one is going to be very similar to, go back a couple slides, it's going to be very similar to the exponential equation property of equality. We're not going to be having exponential equations, we'll be having logarithmic equations, but it works very similarly. It says if the log base b of x is equal to the log base b of y. Very similarly to the exponential equation property of equality. The statement here is that then x is equal to y. Okay, so if we have x is equal to y and we take the log of both sides, it's still going to be equal to each other. Again, the bases need to be the same. They both need to be base b. For these examples, I don't foresee a situation where they wouldn't be the same. Okay, so let's try a couple of examples here. This one should not take very long. So solve number 1. Says natural log of 4x minus 7 is equal to the natural log of x plus 5. So the bases are the same. They're both natural logs, log base e. So if we're taking the natural log of both sides, we can really think of it as they're not there at all. We'll just drop them both and set the insides equal to each other. 4x minus 7 is equal to x plus 5. Okay, 2-step equation, maybe a 3-step here. Get the x's to one side, get the constants to the other, subtract the x to the left, so that gives me 3x, add 7 to the right, gives me 12. 3x equals 12, which means x is equal to 4. Real basic example. Essentially, it's an Algebra 1 problem with ln's in front. If we can just drop the ln's, then it's a real easy problem. Okay, so x is equal to 4 for number 1. Let's try another one here. Number 2. We've got the log of 5x plus 2 is equal to the log of x plus 10. And that's in parentheses as well. Again, same thing, whether it's log base 3, or log base 10, log base e, log base 16, it doesn't really matter. As long as the logs are the same base and they're on both sides, we can drop them. So we're just left with 5x plus 2 is equal to x plus 10. Again, take the x's to one side, constants to the other. 4x is equal to 8. Divide by 4, x is equal to 2. Okay, those types of problems, really not that difficult. All right, final method, undoing a logarithm. So I'm going to go straight to examples, and I'm going to kind of talk you through the first one as far as notes are concerned. So solve. Number 1, log base 2 of 5x minus 17 is equal to 3. So, to undo a logarithm, every time I've asked you to evaluate a logarithm, my answer was always rewrite it in exponential form. Or when you had to graph a logarithmic function, rewrite it in exponential form. We're going to do the exact same thing here with these types of logarithmic equations. We're going to turn this back into exponential form. The base of your log becomes the base of the equation, or the base of your power. The number on the end, what it was originally equal to, becomes your exponent. It's the same rules, we're just rewriting it in a different form. And then what it's equal to is on the other side. So log base 2 of 5x minus 17 equals 3 becomes, 2 to the third power is equal to 5x minus 17. We know what 2 to the third power is. If you're not sure, you can type it in the calculator. You can look at your half sheet. Either one would be fine. 2 to the third power is 8 is equal to 5x minus 17, and now we've got a 2-step equation from pre-algebra. Okay, so 8 equals 5x minus 17. We'll go ahead and, add 17, so that gives me 25. 25 is equal to 5x, which then means x is equal to 5. That's a pretty straightforward example. Hopefully that makes a lot of sense. Number 2, we'll try the log base 3 of 10x minus 9 is equal to 4. Okay, again, rewrite it in exponential form. Your base becomes 3, your exponent is 4, and it's equal to what's left, 10x minus 9. 3 to the 4th power is 81. So 81 is equal to 10x minus 9. Two-step equation here, add 9 to both sides, that gives me 90 equals 10x, which means that x is equal to 9. Those are pretty basic examples. Okay, something a little more difficult. Number 3. Log of 2x is equal to, plus, log of 2x plus the log of x minus 5 is equal to 2. Now, if we've got two logarithms on the same side, what we need to do is try to combine them. And this is the product property of logarithms. If we have two logs and we're adding, we can rewrite it using one log of 2x times x minus 5, and that's equal to 2. This is the product property. I'll write that off to the side. Product property. Property. Okay, product property. So 2x times x minus 5 really becomes log of 2x squared minus 10x, and that's equal to 2. I'm just distributing a 2x to the both sides. Again, let's rewrite this using an exponent, rewriting it in exponential form. When you don't have a base right here, that means it is base 10. So I'm actually going to write it the other way around. 10 to the second power, because this is base 10. 10 to the second power is equal to 2x squared minus 10x. 10 squared is 100, so we'll have 2x squared minus 10x is equal to 100. Now, since we've got a squared, we've got a quadratic quadratic equation. We need x squared, and we need everything on one side. We need it to be equal to 0. Okay, so I'm going to move the 100 over, so we'll have 2x squared minus 10x minus 100 is equal to 0. Now, 2, 10, and 100 are all divisible by 2, so I'm going to divide everything by 2, so that leaves me with x squared minus 5x minus 50. The sole reason for doing that is because I want to work with smaller numbers. I don't really want to have a number out in front of x squared, and if I don't, it makes it really easy to factor. Okay, so we'll have x something is equal to 0. Okay, we need two numbers that multiply together to get negative 50. So in order to have a negative, one's got to be negative, one's got to be positive. So they need to multiply together to get 50 and add together to get negative 5. Since they add together to get negative 5, that means the negative number has to be, quote, larger, meaning farther away from 0. Those two numbers are going to be negative 10 and positive 5, which then means my solutions are going to be x equals 10 and x equals negative 5. If you get a negative answer, chances are that you are probably going to have extraneous solutions. Okay, we can't take the logarithm of a negative number. Okay, but we can go back and check. Okay, so I'm going to use the original equation here. So we'll have the log of 2 times, well, we'll just jump ahead. We'll start with 10. Okay, we're going to start by checking 10 here. 2 times 10, we're going to put it right back in here. 2 times 10 is 20, plus the log of 10 minus 5 is 5. And we're going to see if that's equal to 2. Okay, log of 20, you can type that in your calculator. That's about 1.3. Log of 5 is about 0.7. 1.3 plus 0.7 is 2. Now, if we go back and check, so we know that 10 works. If you go back and check negative 5, 2 times negative 5, log of negative 10. Log of negative 10 plus the log negative 10 minus 5 is negative 15. What you're going to find is you can't take the logarithm of negative numbers. Okay? So generally, if you have a negative answer, it's probably going to be an extraneous solution. Your only answer here for number 3 is positive 10.